Did you know that the chemical reaction used to weld rails together reaches up to 3,500 degrees Celsius? In this video, we're going to be looking at the different ways that rails are joined together to form the track for trains to run on. Rails are manufactured in lengths, but need to be joined together to form the running surface for the train wheels. This can be done in a factory, forming what is known as long welded rails that are then delivered by specialist trains, or more commonly, they are joined on site. Rail joints can be divided into two main classes, mechanical and metallurgical. Mechanical joints are the more traditional type of joint, which includes fish-plated and insulated block joints. Some form parts of the signalling system, while others are being phased out. Metallurgical joints are all different methods of welding the rails together. I have highlighted the common methods that I will cover in this video. Please do let me know in the comments if you're familiar with or used one of the other welding types that I'm not covering. Fish-plated type joints have a long history on the railway and used to be the most common way to join rails. Holes are drilled through the web of the rail, lining up with that of the fish plate. Bolts are then used to clamp the rail between the two fish plates, securing it. The fish plates are designed that only the top and bottom edges actually contact the rail. These surfaces are also lubricated to allow movement. This allows the rail to expand and contract as temperatures fluctuate through the year. The width of the gap is set to a certain measurement, depending on the rail temperature at the time the joint is formed. Ensuring the bolts are correctly tightened is a key maintenance activity, as if they come loose, they could pose a very real safety risk. Fish-plate joints have been phased out on the majority of railways for a number of reasons. The ends of each rail are susceptible to batter and rail defects. The gap in the rail leaves it as a weak point, so it's likely to start voiding, causing track geometry problems. The holes drilled in the rail are also a weakness, with a defect known as star cracking likely to form. This is when cracks initiate from the edge of the hole, radiating outwards. If the crack propagates far enough and reaches the surface, it can lead to a section of the rail separating and falling out. It is caused by both the cyclic loading experienced by the joint and the stress concentration at those holes. A process called cold bolt expansion, where a mandrel is pulled through the hole to expand it slightly, is used to stop this type of defect. This alters the stress around the edge of the hole, reducing the risk of cracks forming. Joints do have their place still though. The most common place to find newly installed jointed track is on curves with a tight radius. This is for a number of reasons, mainly because of the challenges of undertaking stressing on a tight curve. Where pulling the rail, it naturally wants to follow the shortest path, which is straight. There is also the lateral forces during hot weather to consider. Jointed track allows the more pronounced forces to be managed through the length of the curve, given the regular gaps in the rail. Tight joints. Sometimes it's not possible to weld a joint. This can be due to time, how worn the rail is, or the presence of rolling contact fatigue, RCF. A tight joint is an alternative that can be used by maintainers. While a similar concept to a fish-plated joint, with plates either side and bolts through, there's some key differences. Firstly, the ends of the rail sit flush or tight to each other. The second is that this joint doesn't expand or contract. The rail's stressed like any other part of CWR. The last type of mechanical joint we're going to cover is the insulated block joint, or IBJ. These joints can also be called insulated rail joints, or IRJs. These joints, and the location of them, is to support the track circuit signalling system. Track circuits utilise electrical current passed through the rail to determine if a train is in the area of track. IBJs are used at either ends of the section of track to stop the current transferring into the next section. This is achieved with a plastic insert between the rail ends. These joints can be formed in two main ways, either in a factory or on site. Factory-made joints are the most robust and reliable. They utilise a coating to ensure that the joint is fully sealed, which helps stop swarf and other debris bridging the joint and dropping the track circuit. Also, non-threaded fastenings are used, which are stronger and more reliable. You may hear these referred to as factory-made or glued joints. The second construction type is built on site, sometimes called site-mades. This is formed as a normal joint, but with insulated components and an insert placed between the ends of the rails. Insulated joints can also have 4 or 6 bolts, depending on the radius of the track on which they are installed, with 4 being used on tighter radiuses. While there are other types of joints, such as scarf joints, I've covered the main types you're likely to see. You can see that although jointed track is now not the preferred construction type, rail joints do have their place still. As I said earlier, there are a number of different welding processes used to join rails. In this video, I will focus on the two highlighted, as they are the most commonly used. Aluminothermic welding, known by a lot of different names around the world, exothermic welding, thermic welding, or thermite welding, is probably the most common of the type of railway welding. The process uses a chemical reaction, known as the thermite reaction, to create molten metal that then fills a mould that has been formed around the rail ends. When setting up the weld, the welding team will cut a gap around 25 mm wide between the rail ends, into which the molten metal goes. Think of it more as a casting a small section of rail than an actual weld. After a set period of time, a hydraulic shear is used to trim the excess material off, and the weld is then ground down to give a good running surface. The advantages of thermite weld are in its portability. It requires no external sources or machines that cannot be carried on a van or a trolley by a team of 2 welders. It does, however, have some drawbacks. It takes time to set up the mould before the weld can be dropped. This means that short access time, a small number of welds can be achieved by a single welding team. Another drawback is very dependent on the skill of the welders. If the mould is not set up or sealed correctly, the molten metal may run out of the mould. Other missteps in the process can also lead to the weld failing its follow-up inspection. Thermite welds are pretty easy to spot as they bulge out from the rest of the rail. Keep an eye out and see if you can spot them next time you're stood on a platform waiting for a train. Flash butt welding uses electrical current to heat up the rail ends, then hydraulic rams to squeeze them together. No additional material is used to create the join between the rails. The amount of electrical power required to heat up the rails means that the equipment is large and has to be moved with machines. Flash butt welds are of a very high quality and rarely fail. Also, given the more automated process, they are less susceptible to process or operator error than thermite welding. However, high equipment cost and the requirement to be machine-borne and the availability of the equipment has led to low adoption within the UK. An area they are found, however, is in the creation of long welded rails in depots. In these factories, sections of rails are welded together with flash butts into what's known as strings. These vary in length, but a standard length is 180 metres. These can be delivered to site via specialist trains. It's a very efficient way of renewing rails. Other welding types do exist, such as gas pressure and arc welding, but are not commonly used, so I'll not be covering them in this video. So now you know the main ways rails are joined together to form the smooth, continuous surface required for train travel. I hope you found this video interesting and useful. Please do give this video a like and do check out the channel for more on railway engineering. Thank you.